how do we find the mid-segments of this triangle? What do? I find this side, we said it was 10 centimeters. If I put the midpoint on there, what's the midpoint at? If this measures 10 centimeters? 5. So I put it down at 5. I'm like, hey, that's my midpoint. So now these two parts are equal to each other. And this, like we said, would be 5 centimeters. And this one would be 5 centimeters. That's the midpoint of that side. I go to my other side now, and this one was 6 centimeters, so to put my midpoint in here, I need to put my point at 3. Good, Justin. So now this part is equal to this part. Notice I'm not putting one mark in there. I'm putting 2 marks in there to show that these are congruent because I have 3 centimeters and 3 centimeters, which those aren't the same as that. It's just 3 and 5 here. And then 11.5 divided by 2. This is a little tough. Type in your calculator 11.5 divided by 2. What do you get? 5.75. So I come in here. I'm like 5.75. It's like 5.1, 5.2, 5.3, 5.4, 5.5, 5.6, 5.7, roughly right in here. So this part is equal to this part. That's 5.75 centimeters and 5.75 centimeters. Yeah, now we're going to connect them. We have 2 midpoints on each side, and we connect them. And here's my question. What do you know about these 2 segments, these 2 lines? They're parallel. So I'm going to put this one is parallel to this one using the arrows. And if I measure this one, how big should this one be? 5.75 approximately, right? Because this one should be half as big as that one. I'm going to measure it, and I'm going to see what I get. Mine is seriously about 5.75 centimeters. About right under that. Do I have any other mid-segments in there? Yeah. I have these 2 midpoints here. I can connect those. So I know that this line is parallel to this line too, if it's my mid-segment. So watch this. I'm going to put 2 arrows on this one and 2 arrows on that one to show that those are the ones that are parallel. Yeah. If you put your arrows going the other direction, that's okay too. So those 2 are parallel. Here's my question. If this is 10 centimeters, how big should this one be? 5. Measure it. Ah, right on the dot. I'm not making this stuff up. It's really true. When you make your mid-segments, the parallel, one's half as big as the other. And then I connect these 2 dots. So I have this one is parallel to this one over here. If this whole thing is 6, I'm assuming this is 3, but I better measure it and check. Hey, look at that. It's 3 centimeters. It's half as big as that one, and it's parallel. What did we just do? We drew in our mid-segments. Every triangle has 3 mid-segments. So that was the beginning of this week. Yesterday, we talked about perpendicular bisectors. What's the word perpendicular mean? Raise your hand and tell me. Raise your hand and tell me. What's perpendicular mean? Mason? They intersect how? At a 90-degree angle. Raise your hand and tell me, what does bisector mean? I split it in half. I split it in 2 equal parts. Thanks for raising your hand. Here's what we're going to do. We are going to draw a perpendicular bisector. I'm going to come down here. I've got like all this space to work. Roughly in the middle of my white space, I'm going to draw a segment that is 6 centimeters long. I'm going to call this point E and point F. This is 6 centimeters. It's okay if it's crooked. I want to bisect it, and I also want to create a right angle in there. Watch what we do. I take my pointer on the compass and I put it at point E, and then I open my compass a little more than halfway. And here's how you make your life easier. If you hold it up here at this, it's going to be a lot easier to work it and spin it and use it, okay? If you hold it up here, it's going to be easier. So I put it up here, and it's going to be really light, but just do one smooth arc, okay? Do it once and be done with it. So I put my pointer at E, and I open it up to more than halfway. It's not particular, just as long as you're more than halfway. And then just do one smooth arc all the way up. We do it on one side, and then see how I have that measurement? You have to keep that same measurement. And now watch what I do. I flip it around. I still have that same measurement. I put my pointer at F, and I make this half arc circle so that it hits both of them. It's maybe easier to turn your paper and keep your compass where it's at. It's the same measurement on both sides. So what's the point of doing this? Check this out. I have this point up here where they intersect. I'm going to call this G. I have this point down here where they intersect. I'm going to call that H. And then I'm going to use the edge of my ruler, and I'm going to connect them. So let me prove this to you. Look what happens. Take your protractor and see this little crosshair here? There's a hole in it. That hole needs to line up at this intersection right here. We line it up. And then I can measure my angle, but my line doesn't extend quite far enough. So here's what I'm going to do. I'm just going to extend my line clear up here. So now when I measure this, oh, mine's really off. It should be 90. Mine slipped when I did it, so mine isn't quite 90 degrees. But I'm going to do it again, and the next time I do it, I'm sure I'm going to get it at least a little closer than this. So in reality, that should be exactly 90 degrees, and I'm sure some of yours are 90 degrees because you did it right. So that means it's perpendicular. How do I know it's bisected? How do I know this is bisected? Measure it. Prove it. This is 3 centimeters, right? This one, for me, this one is also 3 centimeters. It's bisected and it's perpendicular, right? Flip your paper over to the back where we have more room. You can make yours as big as you want. Maybe we go 12 centimeters this time. Just do it without talking to your neighbor or to anybody else. Let's call this A and B. This was 12 centimeters. So what do? I take my compass. I put the pointer at A. I open it up to more than halfway. And then when I hold it up here and I move my paper, I can make this like half, oh, and see I slipped again, half circle. And I'm keeping that same measurement. I still haven't moved this. I flip it around. I put my pointer at B. And I do it again. And maybe if I call this C and D, I'm hoping when I draw this line through here, I've got a right angle this time. I think mine looks better too. Can you really freehand that? And get it exactly 90 degrees? Alright, so when I measure this, I put my point, that intersection lines up right in that hole. Line it up as close as possible, check mine out. I got 90 degrees this time. I drew my line straighter when I connected my dots. So, is it perpendicular? Yes, it's perpendicular. I had a 90-degree angle when I measured it. And here, is it bisected? Is this part equal to this part? Well, I better measure it just to make sure. This is 6 centimeters. And I hope this one is too. Oh, that's also 6 centimeters. My perpendicular bisector. They intersect at 90 degrees, and it's bisected. Okay? So label it perpendicular bisector. Here's my question. Watch this. You don't need to draw anything else. You don't need to draw in what I'm drawing right now. Just watch a second. And this is where our theorems start to come in. If I take this point C and this point A, what happens if I connect them? Let's see. I connect those, and if I connect C and I connect D, which one of these is longer, AC or BC? Why neither? They should be exactly the same, says John. Exactly. If this is truly my perpendicular bisector, then this part and that part, then this part and this part are equal to each other. How do I know? What happens if I measure it? That's like 3 1/4 inches. Now I'm using inches. Oh well. And that one, oh look at that. That's also exactly 3 1/4 inches. Right? So if this is my perpendicular bisector, then those two parts are going to be equal. Call out your flip book from yesterday. If you weren't here, we'll take care of you in 1 second. Pull this out. Perpendicular bisectors are this. It is perpendicular to a segment at its midpoint. Perpendicular to a segment at its midpoint. Do you remember that symbol for perpendicular? Shorter and sweeter. Perpendicular to a segment at its midpoint. And it also is this. A perpendicular bisector intersects, perpendicular bisectors intersect at the circumcenter. Perpendicular bisectors intersect at the circumcenter. On your folder. Perpendicular bisectors intersect at the circumcenter. Say what? Let me show you. Sketch yourself a triangle. If I draw my perpendicular bisectors, it has to be perpendicular at its midpoint. So I'm like, well, roughly here's the midpoint, so that those parts are equal. And I'm going to have this perpendicular segment in here, so it's similar to that. And then I look at this other side, I'm like, the midpoint's probably in here somewhere, so that these two parts are equal. And if it's perpendicular, I draw in this segment here. Oh, that's not really perpendicular, but it should be. My perpendicular segment here, perpendicular to that side that bisects it, plus. And then this side, I find my midpoint, so that this part and that part are now congruent. And I draw in my perpendicular bisector. And these three perpendicular bisectors intersect at a point. When I have three or more things that intersect, if I have three lines that intersect, if I have three rays that intersect, if I have three line segments that intersect, I say they're concurrent. They intersect, they're concurrent. So specifically, I could say that's my point of concurrency. That's just a general term for it, though. If I want to be specific and I say my perpendicular bisectors are concurrent, my perpendicular bisectors intersect, it just has a fancy name. Instead of saying they're concurrent, I say this is my circumcenter. That point where they all intersect, the fancy name for it is called the circumcenter. And what do you need to know about the circumcenter? It is this. It's the same distance to each of the vertices. The circumcenter is the same distance to each of the vertices. So this point is the same distance to this vertex as it is to this vertex, even though my picture is not drawn right, as it is to that vertex. These three distances in here are all equal to each other. Okay, that's what the circumcenter is. Here's an example, kind of like we did with our homework last night. Sketch a triangle. You guys are doing a phenomenal job following along. Appreciate it. Here's my perpendicular and bisector because it splits it equally. My perpendicular bisector. This is 3x plus 8. And this one is 7x minus 16. So, tell me this. If this is my perpendicular bisector, what do I know about those two parts? They're equal. So set them equal. 3x plus 8 equals 7x minus 16. And solve it. Bring down my 8. 7 minus 3 gives me 4x minus 16. Add your 16 over. 24 equals 4x. We divide by 4. And x equals 6. But are we done? Plug it in. X equals 6, but that doesn't tell us anything about this problem until we plug it in. If I plug it in up here, 3 times 6 plus 8, 18 plus 8 gives me 26. But I want to be positive I got this right, so I don't even have to ask Ms. Rupp. I can answer my own question without a doubt. How do I check it? What? See if they're equal. Plug it in the other one. 7 times 6 minus 16. 42 minus 16 gives me 26. Lovely. Each of those sides are 26. They're equal. I did it right. Okay? on to that. Your theorem sheet. I told you yesterday, look at this theorem on your note sheet, and then they weren't there. They're here. These are all of them for Chapter 5. On your theorem sheet, let's run through this again and again and again. Your midsegment theorem says this. The segment connecting the midpoints of two sides is parallel to the third side, and half as long as that side. Remember, those are parallel, and one is twice as big as the other. 5-2 and 5-3, the perpendicular bisector theorem and the converse of it. Here's what we talked about yesterday. In a plane, if a point is on the perpendicular bisector of a segment, if a point is on that perpendicular bisector, then it is equidistant. What's equidistant mean? Equal distance, the same distance, right? Then this point is equidistant from the endpoints. So this distance and that distance would then be the same. The converse of it, if a point is equidistant from the endpoints, then it is on the bisector. So I look at this, I'm like, if this distance and this distance are the same, then that point will lie on that perpendicular bisector should I continue that line. Okay? Keep going. This word again, concurrency. It's not congruent. Turn all the way around and face the front. You're in your focus. Concurrency of perpendicular bisectors of a triangle. What does concurrent mean? Raise your hand and tell me. Concurrency basically means just the fact that they intersect. Concurrency of perpendicular bisectors, it's really saying the intersection of perpendicular bisectors. Make sure you get that down because you can use this. Concurrency just means the intersection. Where do the perpendicular bisectors intersect? Perpendicular bisectors of a triangle intersect at a point equidistant from the vertices. So here's a perpendicular bisector. Here's a perpendicular bisector. And here is a perpendicular bisector. At place they intersect, what do we call that point? The circumcenter. The circumcenter is the fancy specific name for it. Just in general, I could say, hey, those lines are concurrent. They intersect. Or that's my point of concurrency. But specifically, we want to refer to it as a circumcenter. The circumcenter is the same distance to each of the vertices. So this is equal to this, which is equal to that. Got it? 5-2A. Number 5. In the diagram, perpendicular bisectors of M and P meet at point O and are shown dashed. I'm telling you the perpendicular bisectors are the dashed ones. Find the indicated measures. Here's what I'd suggest. If you go through, you're going to start and you're going to get on a roll and you're going to be like, I know these parts and those parts and these parts. Label everything you know about the picture first and then go back and answer the questions. If this is my perpendicular bisector and this is my perpendicular bisector and that is, what do we know about this point O? That's called the circumcenter. And what's special about the circumcenter is this. This distance to each of the vertices is exactly the same length. Do I know what any of those lengths are? None of them? 26.8. This one's 26.8, right? And this one is going to be 26.8. And this one is also going to be 26.8. See, like I say, you get on a roll, you label everything you have, and then those questions are going to be a piece of cake. What else do we know about perpendicular bisectors? If this is my perpendicular bisector, what does bisect mean? Cuts equally in half. So this bisector splits this side into two equal parts. If that's 22, how big is this one? 22. If this is my bisector right here, if that's 26, this is 26. Sorry. If that's 26, this is 26. I see where you're going with that. If this is 20, this is 20. We just labeled like everything real quick right off the bat. It's like those are equal, Those are equal. Those are equal. These lengths in here, I haven't taught you how to find yet, and we're not, at this point, we're not going to find those just quite yet. That's right. That's right. So now, answer your questions. Number 5, MO. Where's MO? MO. This distance right here is 26.8. PR. PR is right here. We have 26. Oh, look how quick this goes. MN. We've got 20 and another 20. Gives me 40. Number 8. SP. S to P is 22. QN. Q to N is 20. And MP. M down to P, I have 22 and 22. Gives me 44. See how quick that is? Quick and easy. Boom. 11 and 12. Tell whether the information in the diagram allows you to conclude that C is on the perpendicular bisector of AB, and explain. Is C going to lie on that bisector? How do you know? We're just guessing? What theorem does it look like? The first one or the second one? 5-2 or 5-3? 5-3. Why 5-3? If we take this and I flip it upside down, doesn't that look I flipped my paper upside down, doesn't that look exactly like this one? On my paper, I'm like, when I turn my paper upside down, I'm like, those two parts are marked congruent just like this. I've got these two parts are marked congruent just like there. I've got it's perpendicular. So here's the thing. What does that theorem say? That was theorem 5.3, right? What's the theorem say? The theorem says this. If a point is equidistant from the endpoints of a segment, if a point is equidistant from the endpoints, is that true? Is this point the same distance from each of those endpoints? Yeah. Then it is on the perpendicular bisector. Oh, it basically just told me the answer. So, enough information? I say yes. How do I know? By theorem 5.3. And I say yes because AC equals BC. Why does C lie on this line? Because this segment and this segment are equal to each other. Number 4 here. Is there enough information to conclude C lies on the perpendicular bisector? No. Enough info. How about number 5?